In this video, we're going to talk about the central limit theorem, and it's a very crucial topic in inferential statistics. So it's kind of a pretty important thing to learn about. Now, the first time that you listen to me or read about it, it might be a little hazy for you. It's kind of hard to wrap your head around it because it's kind of got to think in hypotheticals. So this is really different than anything we have done before. Before we just did descriptive statistics, and now we're jumping into inferential statistics, and we're still not even all the way there yet, but you kind of got to grasp your head around this idea to get there. So you might need to kind of let this sink in a little bit before you really get to understand it. So to understand the central limit theorem, we need to understand what a simulation is. So a simulation is where statisticians make up this population data to make these theorems, these rules. So normally we don't have all the population data, right? That's really rare that we have all the data for our whole population, unless our population's really small, like your family, then maybe you have all the data that you want, but that's never the case. Usually you want to know about people in general. If you want to know about people in general, we need to survey everyone in the world. And you can never do that, right? So they make up these big, huge data sets, huge ones, and they give them some kind of distribution, some kind of shape, and a certain mean and a standard deviation. And then they test it. They test it by taking random samples from this big made-up data that they have in Excel or some other statistical program, and they do some tests on it. And when they do these tests, then they can make up these rules that we can go by when we actually take samples from real people in the real world. So we base these rules on these simulations that we do with kind of fake population data and see what happens when we take samples and how that compares to the actual population. And then when we don't have the whole population, we can use these rules as kind of guidelines about how these samples will compare to the actual population that we don't really know about. So hopefully that kind of makes sense. So again, we have fake population data that we make up. We do some tests by taking random samples. We compare the random samples to the actual population. So like we see if the mean's different, we see if the standard deviation is different than these samples and the population between and between the samples. And then when we actually take samples in the real world, then we can use those rules that we made doing this simulation to make what are called inferences about the population with only our sample data, because we don't have the population data usually. Okay, and so we're going to make inferences in inferential statistics. That's why it's called inferential statistics. So these are statements about the population based on only a small sample. So we're not 100% sure about our inference, but we can kind of quantify our sureness with some kind of probability. And we'll get to that in more detail later. That's just kind of the mindset you need to get into. We're going to be doing a central limit theorem simulation. Okay? And you're also going to do that for your homework a little bit as well. So hopefully that'll kind of help you understand what the central limit theorem is. So here we have a population distribution, right? So remember, a population is everyone that you're interested in, okay? It's not just a random sample of a few people. And it's a uniform distribution. And we're going to end up drawing samples from this population that has a uniform distribution. So we're going to randomly select people in a minute. And we can just pretend that this population is really big. It's like 1,000,000 or some big number, okay? It doesn't matter too much. And the scores in the population range from 1 to 5. You can see that. And you probably guessed the mean of the population is 3. It's right in the middle, and it's a uniform distribution. Symmetric. So you can probably guess that the population mean is 3. And we also have a population standard deviation of 1.41. Okay? This is our population. And we're going to start with a small example of the central limit theorem and then kind of build on it. It's going to start with a small simulation, then build on it so we really understand the central limit theorem. So we're going to start small and draw 6 samples randomly from the uniform population that was presented on the previous slide. So remember, in this uniform population, we have a lot of scores, maybe 1,000,000 or so, and we're going to randomly select 6 samples. And each sample has 5 subjects. So their sample size, or n, equals 5. Central limit theorem requires that all samples must have the same sample size. So in summary, we're going to have 6 samples, each with n equals 5. We're going to have random selection. So remember, random selection is basically the equivalent of pulling names out of a hat. Now, it doesn't have to be done in that way, but it has to be the same as if we were going to do that. So random selection, by its definition, is each person has the same chance of being selected. Okay? And so drawing names out of a hat is one way to do that. There's other ways, like computer programs or things like that. Okay, so we randomly selected 5 people per each sample, and we have 6 samples. So we randomly drew 5 people for sample 1, and the first person had some score of 5, the second person had another score of 5, and the third person had a score of 5, and the fourth person had a score of 4, and the fifth person had a score of 3. In the first sample 2, the first person had a score of 1, the second person had a score of 2, the third had a score of 5, the fourth had a score of 3, and the fifth had a score of 3. And then you can see that continues through all these samples, okay? So you have 6 samples, each with an n of 5, and we randomly selected these people. Now we're going to find the sample mean for each of our samples. The first sample had a sample mean of 4.4. The second one had a sample mean of 2.8. The third had a sample mean of 2.4. The fourth had a sample mean of 3.4. The fifth had a sample mean of 2. And the last sample had a sample mean of 2.4. Now we're going to find the mean and standard deviation of our sample means. So the mean of the sample means is 2.9, and we're going to denote this with this mu, that like squiggly looking M thing that we've been using for the population mean. But we're going to put a subscript of x bar by it. So that just means it's the mean of the sample means. And that's going to equal 2.9. So I just took what we have down here, the sample means, and found their average, okay? And then I also found the standard deviation of these sample means, and that was 0.8. And this is called the standard error. The standard error is the standard deviation of the sample means. And we're going to denote this with sigma, which is what we usually use for the population standard deviation, but we're going to put a little subscript of x bar by it. So this is the standard error when we have sigma with this little x bar as a subscript. And so that's the standard error, which is the standard deviation of the sample means. It's 0.80. And we're going to compare this to our population parameters. So these parameters were what we had for the uniform distribution. So remember, our population had a mean of 3 and a standard deviation of 1.41. So you can see that the means of both the population and the mean of the sample means are approximately equal to each other. And we can also see that our standard error is less than our standard deviation from our original population. And that kind of makes sense that the standard error would be less, because if you look at these numbers here, there's more variability in the individual scores from our population, right? So in our samples, you could have 1 through 5, because in the population that's what the numbers were, 1 through 5. So there was a range from 1 to 5. And then, but for our sample means here at the bottom, the lowest one was 2, and the highest one was 4.4. And so the range from 2 to 4.4, and that range is some sort of measure of variability. So 1 through 5 is more variability than 2 to 4.4. So it makes sense that also that our standard error is less than our standard deviation here. Now I'm going to make a frequency table of our sample means. We had no sample mean that was between 0 and 1. And so we put a 0 there. We had one sample mean that was between 1 and 2. So we're going to put 2 in that bin there. And then for 2 to 3, we had 3. So we have the 2.8, the 2.4, and the 2.4 at the end here. So we're going to put 3 for that frequency, for that interval. And then for the interval 3 to 4, we have 1, which is sample 4, which has a mean of 3.4. And then for 4 to 5, for that interval, we only have 1, which was 4.4, which was for sample 1. Now, after we make a frequency table, we're going to make a histogram of these sample means. And the histogram of the sample means is called a sampling distribution. And so you should know what this term is. So sampling distribution is a histogram of the sample means, or a distribution of sample means. So here we're going to make the histogram. There is no one in the first interval, but there was a sample in the second one. So we're going to go up to 1 there. For the 2 through 3 interval, there was 3 samples. So we're going to put the bar up to 3 there. And then for the interval 3 to 4, we had 1 sample mean in the interval. And we also had 1 sample mean in the interval 4 to 5. And so now we have a histogram of our sample means, which is called a sampling distribution. I said that we were going to start with a small kind of example and then kind of amp it up later. So I was just going through all the steps of making a sampling distribution and finding the mean of the sampling distribution and the standard error of the sampling distribution. And so now we're going to kind of amp it up a little bit and add 19 additional samples, but we're not going to be as detailed in how I show you this. And so here are our sample means. So it has the original 6 and it has 19 more. So we have a total of 25 samples, but still each of them have a sample size of 5. So each of these little blocks, each of these cells represents a sample mean of a sample of 5. Okay, and then there's 25 of them. And I'm just going to skip through the frequency table here, but go ahead and make a histogram from that frequency table. And also find the mean of the means or the mean of the sampling distribution, and that was 3.14. And I'm also finding the standard deviation of it, which is called the standard error. And you can see that is 0.59 here, according to this chart. You can see now we're getting even a more mound-shaped distribution. Okay, so remember that this came from a uniform population, right? Our population distribution was uniformly distributed. But then after we're taking the samples and then finding the sample means and making a histogram of that, you can see it looks more mound-shaped. It doesn't look uniform anymore. We can also see that the mean is approximately equal to the population mean, and the standard error is less than the standard deviation from the population. So the same thing kind of happens when we take more means, but it starts to look even more normally distributed, more mound-shaped here. So now on the next slide, we're going to see what happens when we take 100 samples. So now it even looks more normally distributed, right? It's getting filled in. The more samples we take, the more filled in it's going to look. And the mean is 3.11, which is about 3, which was the population mean. And again, the standard error, or the standard deviation of the sampling distribution is 0.63, which is still less than the population standard deviation of 1.41. And remember, these sample means were taken from a uniform distribution, and it looks nothing like a uniform distribution anymore. It looks more and more normally distributed. Now, we can see that this distribution of sample means is even closer to a normal distribution than the distributions calculated with 6 and 25 samples. So the more samples we have, the more normally distributed it's going to look. And the mean of the distribution is quite close to the population mean of 3. And the standard deviation of the sampling distribution, which is called a standard error, is smaller than the population standard deviation of 1.41. So that's kind of what we learned so far. Now we're going to increase the sample size, and we're going to really focus on the sample size, so the sample size of each individual sample. And that's more important to think about than how many samples we have, okay? So we're going to increase our sample size from 5 to 25. So now we have 25 sample means, but instead of each of them having a sample size of 5, now each of them have a sample size of 25. So we're going to look at these two histograms and compare them. Okay, so there's, on the left-hand side, we have 25 samples. Each have an N of 5. And on the right-hand side, we have 25 samples. And we're going to keep the number of samples consistent because we don't really care about that as much, okay? But what is different is the N of 25. So each sample in the second histogram on the right, each sample has an N of 25, okay? So what do you notice? Well, they both have about a mean of about 3. The second one is a little bit more accurate. It's a little bit more closer to the mean, 3.02. That makes a little sense, right? If we have more information, if we have higher sample sizes for each sample, right? You would think the mean would be more accurate when we have 25 people in our sample versus when we have just 5. So that makes sense that our mean is more accurate. But we also see that our standard deviations, called our standard errors, is smaller when we have a bigger sample size. So that kind of makes more sense. If the means are more accurate, right, with more information, with a higher sample size, then they're going to vary less from each other. Okay? Now we're going to compare these 4 histograms. So this top one here is our population distribution that we started with. So it looks boxy like this. It's a rectangle shape. Each value has an equal chance of being selected, and we have, about 1 million people in this population. We'll just say that. And then we have a mean of 3 and a standard deviation of 1.41. Now in this first sampling distribution, this one, we took an infinite amount of samples, or a really big amount of samples. The amount doesn't really matter. What really matters and what you really should focus on is the n. So for each sample, we have an n of 5 for this distribution. And then for this distribution, we took an infinite amount of samples, but each had an n of 25 for this one. And then for this one, we had an infinite amount of samples. Again, that doesn't really matter. What really matters is that our n is 100 now. So what do we notice? Our means for our sampling distributions are equal to 3. And that is equal to our population mean. What we also notice is that our standard errors here, which is the standard deviation of our sampling distributions, are all less than our population standard deviation of 1.41. And what you also should notice is that as we increase our n, our standard error decreases. So when we had n equals 5 here, we got 0.63. When our n was 25, we got 0.28. And when our n was 100, we got 0.14. And you can see that on the histograms as well. It's depicted there. Our histogram gets squished in more and more as the n increases. And that's because our sample means get more and more accurate. We are more consistent. So when we have just an n of 5, sometimes we're going to get a sample mean that's 5. It's just out there because it's only based on 5 people, and so sometimes you're just going to get sample means that aren't very accurate of the population mean, and then sometimes you are just by chance. And then, but the more and more people you have, the higher the sample size you have, the more likely the sample mean is going to be accurate. So we're going to have a smaller and smaller standard error. And so things are going to be, the sample means are being closer and closer to each other. Now here's an example with a Poisson distribution. You don't really need to know what a Poisson distribution is. It's just one that's skewed to the right. But let's say we had this Poisson distribution, or a skew to the right distribution, and that's our population distribution. Say we had a mean of 0.78, and a standard deviation of 0.90. And then we took a lot of samples of n equals 5 here. We made this histogram. And then we did it with n equals 25. So we have a lot of samples of n equals 25. And we made this histogram. And then finally we have n equals 100. So we took a lot of samples with n equals 100 and made a histogram of its sample mean. So these are the sampling distributions. So these are the histograms of the sample means. So the means again for the sampling distributions here, they're all around our, our population mean of 0.78. I mean, they're exact. And then we see that our standard errors here, our standard deviation of our sampling distributions, are all lower than our population standard deviation of 0.90. And we also see that again, as our n increases, so we go from 5 to 100, our standard error, which I'm going to put as SE, decreases. So we go from 0.40 for n equals 5 to 0.18 for n equals 25, and we go to 0.09 when we have n equals 100. So you can see that the central limit theorem also works for Poisson or distribution or skew to the right. In fact, it works for any distribution. So we went over two examples, the uniform and the Poisson. So it doesn't matter how the distribution is before for the population distribution. It just matters how many, and you take